Nvidia designed the most powerful AI processor ever built. Two GPU dies side by side, a 250 billion transistors, more compute in a single package than most data centers on Earth could deliver a decade ago. But Nvidia does not make it. Nvidia cannot make it, because making a chip like this is no longer a single step. There is design, there is fabrication, and then there is assembly, the step where you physically bond everything together into working package. That assembly step is controlled by effectively one company, and that company also packages the chip inside your MacBook, your iPhone, and every server that answers when you talk to ChatGPT. Their packaging line is sold out through 2027. Welcome to Growth. I'm Sean, your guide to money and navigating the frontier of innovation. Today, we're going to break down why AI chips cannot get any bigger, the physics of the packaging technology holding the entire AI revolution together, and why the most overlooked choke point in the AI economy is not a chip designer, not a software company, not an energy contract. It is a packaging line in Taiwan. TSMC, a Taiwanese company that manufactures chips for Nvidia, Apple, and nearly every leading AI company, is spending $52 to $56 billion in capital expenditure this year, the largest single-year spend in their history. They quadrupled their advanced packaging capacity in 2 years, and they are still sold out. I want you to sit with that for a second. The largest capex in the history of one of the world's most valuable companies. Quadrupled capacity. Still not enough. That is not a supply chain problem. That is a structural physics problem. So let me start with a question almost nobody asks. If an AI chip needs more power, more transistors, more compute, more memory bandwidth, why not just make the chip larger? The answer is a physical constraint that has been baked into semiconductor manufacturing for 60 years, and it is absolute. Every chip starts as a silicon wafer, that large circular disc you have seen executives hold up for cameras. But the wafer itself is not one chip, it is a canvas. The same circuit pattern is stamped onto it hundreds of times in a grid, each stem producing one die. Those dies are then cut apart and packaged individually. Each stamp uses ultraviolet light passed through a patterned mask called a reticle, focused down by a lens onto the wafer surface. That lens has a fixed physical aperture, roughly the size of a postage stamp. And because scaling that aperture destroys the optical precision required for nanometer scale circuits, each die is fundamentally limited to the area the lens can cover in a single exposure. That is the reticle limit. Not a manufacturing choice, but an optical constraint. AI changed the scale of the problem completely. A modern AI training chip needs to fit thousands of parallel processing cores simultaneously, a scale that consumer devices, no matter how powerful, simply cannot match. The only path forward is to place enormous amount of memory physically adjacent to the processor, connected by the shortest possible path. That demands silicon real estate, a lot of it. The H100, the B200, Google's TPU, every leading AI accelerator built in the last 3 years has slammed into the same wall. The Nvidia H100 already occupies 814 square millimeters, nearly every millimeter of available optical exposure. There was nowhere left to go. So the industry made a choice. Instead of one giant die, build several smaller ones and connect them on a shared platform. The B200 is 2 GPU dies side by side, together exceeding the reticle limit by roughly twice. The Rubin R100 pushes further. 2 GPU dies plus 8 stacks of next-generation memory on a shared silicon floor that spans 4 times the reticle limit. The chip is no longer a chip. It is an architecture. And that architecture cannot exist without a packaging technology that most people have never heard of. 2 dies sitting side by side. It sounds like an assembly problem. Put the pieces together, connect them, ship it. It is not that simple. The moment you place 2 chips next to each other and try to connect them at the speed AI requires, you run into a new set of physical constraints. You need a shared platform precise enough to position dies within nanometers of each other. You need interconnects dense enough to carry terabytes of data per second between them. And you need all of it to hold together under the thermal stress of a chip drawing hundreds of watts. That platform is called an interposer. And the technology TSMC uses to build the entire stack, interposer, dies, memory, is called CoWoS. CoWoS, chip on wafer on substrate. Substrate at the bottom, silicon interposer in the middle, compute dies and memory on top. And here is why that middle layer changes everything. In a conventional server, a GPU and its memory sit on a printed circuit board, connected by copper wires. The distance between the processor and the data it needs is measured in centimeters. That distance costs energy. Energy becomes heat. And because AI workloads are not limited by how fast the chip calculates, they are limited by how fast data can be fed into it. That heat is not a side effect. It is the bottleneck. CoWoS eliminates that distance. The GPU dies and HBM memory stacks are bonded directly onto the interposer, side by side, millimeters apart. The data no longer travels across a circuit board. It travels through silicon. The path shrinks from centimeters to microns. The result? Dramatically more data, moving faster, generating less heat. So far, this sounds like an engineering solution. And it is. But the problem is what happens next. When you run current through this package, everything heats up and everything expands, but not at the same rate. Silicon barely moves when it heats up. Copper expands nearly 7 times faster. Now, imagine bonding 2 materials together where one side wants to grow 7 times faster than the other every time the temperature rises. On a small package, the stress is manageable. But the B200 interposer spans roughly twice the reticle limit. A silicon tile the size of a small coaster. At that scale, the mechanical stress does not grow linearly. It grows with area. The forces trying to peel those nanometer scale bonds apart become enormous. Nvidia's first Blackwell production run experienced exactly this. Warping that killed yields and forced a redesign. That is not a quality control failure. That is what happens when you push a silicon tile twice the size of anything built before. And then there are the TSVs, through silicon vias, the vertical channels that carry signals through the interposer. Each one is a hole drilled through silicon with a diameter roughly 1/10 the width of a human hair and a depth 10 times its width. Think of drilling a hole the width of a strand of spider silk through 20 floors of a building, then filling it with copper without leaving a single void. One bubble, one misalignment, and the signal degrades. Now do that tens of thousands of times across a single tile at yields high enough to be economically viable. This is where the real moat lives. Not in the design, not in the patent, in the data, years of failed wafers that taught TSMC exactly where the process breaks and how to stop it. You can write the check, but you cannot buy that. TSMC's advantage here is scar tissue, which means packaging is no longer the back end of semiconductor manufacturing, the low precision step after the real work is done. It is now as technically demanding, as capital intensive, and as strategically critical as fabricating the chip itself. The market has known about this bottleneck since 2023. What it has not internalized is that 2 years of record capital expenditure and the demand it unleashed has kept the gap exactly where it was. Now, let me show you what happens when a technology becomes both essential and nearly impossible to replicate. TSMC is the only company in the world that can manufacture CoWoS at the scale and the precision required by the leading AI chips. Nvidia's Blackwell and Rubin, Broadcom's custom silicon for Google and Meta, AMD's Instinct line. So, what does demand look like against their capacity? In late 2024, TSMC's CoWoS capacity was approximately 35,000 wafers per month. By the end of 2025, they reached 75,000. Their current target for end of 2026 is 130,000. That is nearly a 4 times expansion in 2 years. Aggressive by any standard in this industry. And it is still not enough. Morgan Stanley estimates that Nvidia alone will require approximately 595,000 CoWoS wafers in 2026. That is 60% of total projected global capacity. Add Broadcom and AMD, and over 85% of TSMC's available packaging capacity is already pre-committed by a handful of chip designers. And here's what most coverage of this bottleneck misses. The 85% is not just data centers. It is not just training clusters. It is also the device in your pocket. Apple's M-series chips, the silicon inside every MacBook, iPad, and Mac Studio, are packaged by TSMC using advanced packaging processes that shares the same fab infrastructure as CoWoS. Apple's private cloud compute servers, the backbone of Apple Intelligence, run on custom Apple silicon packaged by TSMC. When you ask Siri to summarize your email, the chip that processes that request, whether on your device or in Apple's servers, came off a TSMC packaging line. TSMC is not just the bottleneck for AI data centers. It is the bottleneck for the entire AI compute stack, from the largest GPU cluster to the thinnest laptop. Now, add geopolitics. Every front-end CoWoS facility in the world is in Taiwan. TSMC is building packaging capacity in Arizona as part of its US expansion, but it will not be operational until 2029 at the earliest. For the next 3 years, the compute build-out of the Western world, the AI chips powering the largest infrastructure investment in human history, and the consumer devices delivering that intelligence to billions of people flows through packaging lines on a single island. The obvious question is, why doesn't someone else build this capacity? 2 serious players are trying. Intel's approach, called EMIB, skips the full silicon interposer entirely. Instead of a shared floor connecting everything, it uses small silicon bridges, only where chips actually need to talk to each other. Simpler, cheaper, and easier to scale to larger package sizes. For chips that don't need the extreme bandwidth of a GPU training cluster, it works. Google and Meta are already evaluating it for their custom silicon. But for Nvidia's Rubin, where thousands of cores need to feed on terabytes of data per second, the physics still favor CoWoS. Samsung's pitch is vertical integration. They make the HBM. They design the packaging. They optimize across the entire stack. In theory, a structural advantage over a pure foundry. Their solution, called iCube, has been on the roadmap since 2018, but a validated, high-volume customer at Nvidia-level complexity does not exist. The pitch is compelling. The proof is not. The gap will narrow. Intel is serious. Samsung has the long-term incentive. But on the timeline that matters, 2026, 2027, 2028, there is still one phone call to make. For 50 years, the semiconductor industry ran on one story: Moore's law. Shrink the transistor. More compute per dollar, per watt, per square millimeter. The fab was everything. The node was the moat. 7 nanometer, 5 nanometer, 3 nanometer. Those numbers were the scoreboard. That story is not over, but a second story has joined it, and the market has been slow to read it. Performance gains in AI are no longer coming primarily from shrinking transistors. They are coming from how you connect chips together, from the density of the interposer, from the precision of a bond measured in nanometers, from the yield data accumulated across millions of failed wafers. The value in the semiconductor stack is migrating from transistor density to interconnect density, from the die to the package, from the front end to the back end. When TSMC quadruples its packaging capacity in 2 years, and it is still sold out, that is not a temporary supply chain imbalance. That is a structural signal. The bottleneck has moved, and capital will follow. The companies that control advanced packaging are not service providers. They are gatekeepers. Without a validated CoWoS line, the most sophisticated chip design in the world is just a PDF file. It does not generate revenue. It does not power a data center or an iPhone. The physical constraint has moved. I want to leave you with one thought that goes beyond the supply chain. For most of human history, the scarce resource in technology was the idea, the blueprint, the algorithm. We assumed that once you had the design, manufacturing was the easy part, a cost to be minimized, a process to be commoditized. What CoWoS tells us is that assumption is breaking down. The physical act of assembly, bonding two dies together within nanometers of precision, managing the thermal stress of materials that want to tear themselves apart, filling microscopic channels with copper without a single void. That is now where the value lives. Not in the idea, in the execution. We are entering an era where the most strategically important companies are not the ones who design intelligence, but the ones who can physically build it. That is a different kind of moat than the market is used to pricing. The packaging war has a clear leader today. Whether it stays that way is one of the most consequential industrial questions of this decade. This was Sean from BuySpark. If you enjoyed the video, press like, subscribe, and don't forget the notification. And if you want the deep dive report with the full citation and market breakdown, subscribe to our newsletter at the link below. Thank you for watching. Until next time.